All right, I'll get started here. So the material I should share with you now is not on the test or the quiz Friday. But actually, before I do that, are there any questions about the material we've covered already?
Friday, we'll get here at 12:30 drawing. The quiz being
So, yeah, I think, will the quiz be shorter? I mean, I suppose so. But I will try to make sure we get the full time for the test. So, like it'll be next Wednesday, right? So we're into chapter 4, which is on exponential functions and logarithms and all that. So let me begin with a definition. So exponential and logs. I mean, that's basically the next topic. And so here's a definition. The exponential function with base A is defined by f of x equal a to the power x, where a is positive and a is not equal to 1. Huh. Interesting. So let me just try to dig into this a little bit. So for example, if we choose base 2, right, then we can look at f of x equals to 2 to the x, right? And we can try to understand what this means, right? So let's just think about a table of values here for a second. So here's my x, here's my 2 to the x. So if I put in minus 3, I have 2 to the minus 3. What's that mean? That's 1 over 2 cubed, right? Which is 1/8, right? Could try, say, minus 1. 2 to the minus 1 is what? It's 1/2, right? So what's that in terms of decimals? Well, the half is easy enough. That's 0.5. What's 1/8 in decimals? 0.125. Very good. It still counts. 0. So 0, what's 2 to the 0? It's 1. 2 to the 0 is 1. It's okay. 2 to the 1. What happens if I plug in 1? 2, right? Continue this list up here. X, 2 to the x. All right, great. What if we put in 2? All right, well, 2 to the 2, which is 4. What if we put in 3? 2 to 3 is 8. All right, great. What if we put 2 to the 1/2? What's that?
2 to the 1/2.
Mm-hmm.
So it's 2.
What's our other note? I'm an idiot. I meant 1/2 here.
Oh, okay.
Sorry about that. Yeah. I mean, you could do that, but this is what I intended. And that's what? That's the square root of 2, which is what? Approximately 1.414, right? But the thing is, I mean, so we can keep on, basically, let me just put it more in general. If you have x is p over q, where, you know, p and q are integers, then what's 2 to the p over q? What's that equal to? I mean, how is that defined? It's the qth root of 2 to the p, right? So as long as you're thinking about a rational exponent, we can calculate 2 to that power just by either like raising it to a power or taking a qth root, right? But notice that I've defined a to the x for any, this is for any real number. So everything in my examples so far, these have all been rational inputs. What would we mean? What would it mean, like 2 to the pi, for example? What would that even mean? What's 2 to the pi? Like, you can't calculate that in terms of a root, right? It's just, but what is that? And how do you understand that? Like, what is that value? I don't know if you've ever thought about this before, but if you want to think about it approximately, you could say, yeah, well, what's an approximation for pi as a rational number? What is it? 3.14? So you're telling me 314 divided by 100, right? Or oftentimes people like to use 22/7. That's like a pretty decent approximation for pi. Try it out. (22 divided by 7 is 3.1428, blah, blah, blah. So it's got the 3.14. And so like 22/7, I could calculate that. That's the 7th root of 2 to the 22 power. I mean, so this is actually more or less the idea. To extend the value of exponentials off the rational numbers, any real number you can think about as being very close to a rational number, right? So the fact that we can define 2 to a power for a rational power means that we can approximately define for close by real numbers which are not rational. But anyway, so to make that rigorous, you know, take a course in real analysis or something. I don't know. So I just wanted to mention that. That's kind of just for your information. But what's more interesting, of course, is to graph 2 to the x. In other words, what I'm saying is you could imagine like plotting the values of 2 to the x using the rational inputs and then just kind of connect the dots, and that would be everything else, you know. 22/7 is somewhere, what is this equal to? 2 to the pi. It's approximately what? 2 to the 3.14, which is kind of close to 8, right? So anyway, getting to the point here. So if this is 1, so it's at 0 it's 1, at -1 it's a half, at -2 it's an eighth, and so forth, right? At 1 it's 2, at 2 it's 4, and at 3 it's, well, it's starting to get way beyond where I can graph, right? So exponentials, they grow at ever increasing rates, right? Like, it's the way it works. So this is y equals 2 to the x, right? So I've just put some key points in here, like this is 1, 2, and this point here is 2, 4. This point over here, minus 2, 0.25, right? All right, well, so actually, rather than continuing this method, let me use the projector over here if it's working. Hopefully it's working. Oh, yes, please, thanks. I know, I seem to have forgotten my zip drive of attendance. Let's see here. All right. Go away, smartboard. All right, so let's look at y equals 2 to the x, 2x, good job, 2 to the x. All right, so here this is called an exponential function in part because the variable is in the exponential, right? The base is fixed, right? In contrast, a power function, the variable is in the base and the exponential is fixed. But they're both really the same kind of formula, right? You know what I'm saying? Let me write it out. So f of x equals a to the x is an exponential function. But if we look at g of x equals, x to the n, this is called a power function. But really, when you get right down to it, it's the same, really the same formula, right? It's a number raised to another number power, right? It's just that we typically look at n being a whole number, whereas a here doesn't have to be a whole number. Like we can look at bases other than 2. But here's the graph of 2, right? I think what's interesting to look at is what happens when we change the base, right? So I'll keep 2 as a reference point, right, as a reference graph, if you will. And I'm going to add another picture here, y equals a to the x. We'll add a slider. All right, so this is a equals to 1. So you can see why the definition wants to rule out 1, right? Because 1 to the x is a very boring function. It's just the constant function 1, right? So that's why the definition doesn't allow 1. If you put a negative, watch this. It can kind of make sense of some stuff, but it's very sketchy, right? Like you see there's some dots in there. Let's just say that negative bases are hard to understand, okay? So we don't want to think about that. We'll leave that to your complex analysis class. The base 0.1 power, look at that. The 0.1 power, that's interesting. Why would that be? Why is it that if the base is 0.1, it looks like this? Here, let me add yet another one. Let's look at to the 10x, see if you can see any relation between the 0.1 and the 10x. So the 10 to the power x is the steep dark blue one. The 0.1 is the lighter blue one that goes like that. What's the relation? You see they're the same graph, they're just reflected one over the other? Right? Why is that? What's going on? Let's think about it algebraically here for a second. F of x equals 0.1 to the x is equal to 1 over 10 to the x, right? But by laws of exponents, that's 10 to the minus x, right? So what is 10 to the minus x? If you think about the graph y equals 10 to the x, with x switched to minus x, we get y equals 10 to the minus x, right? And what is that? That is a reflection over the y-axis, right? If we swap the input for minus the input, then we reflect over the y-axis, and that's what we're seeing here with the 0.1. So what I'm trying to say is, if you think about it, if the base is between 0 and 1, you're going to have stuff that looks kind of like the dark blue graph. Let me get rid of the purple one here. So check it out. Let me switch up my values for the step. Let me go from 0 to, let's say, 4. So I have a nice, how many steps should I take? I don't know, 200. There we go. All right, so, come on. Hey. Oh, wait a minute, what have I done? I did something bad. Oh, this is the step size. Can you go with a step size of 200 from 0 to 4? It's not the number of steps, it's this step size. So like, I really would like 0.01 or something like that, you know? All right, there we go. So check out what happens. See, it all kind of got the same shape, right? When we get to a half, it should match the one that we currently have, which is 2 to the x, right? But it should be reflected. You see that? See how there's a perfect reflection between the 2 to the x and the 1/2 to the x? It's the relation between the two. And see, this will continue to look like that right up until we get to 1, right? And then when you get past 1, see what happens? It starts to resemble the 2 to the x. See that? Of course, when we get to 2, it'll match up exactly. See that? And then here we're getting up over here to 3 to the x. It's like right there, right? So that's what we have to look forward with these exponential functions. This is what their graphs look like, right? This much I can tell you. There's, what can we say common to all exponential functions? What's the y-intercept for any exponential function? 1, right? And they also sort of have a horizontal asymptote, but I would say it's one-sided. I don't know if we have that language in your book or not, right? But the rational functions we've been looking at, we have the same asymptotic behavior to plus infinity and to minus infinity, right? If it goes to 1, it goes to 1 on both sides. If it goes to 0, it goes to 0 on both sides. But the exponential will only go to 0 on one side or the other, right? Like depending on whether the base is less than 1 or greater than 1. And so we just sort of summarize what we've just learned or seen. There's really three, I would say there's 3 cases, but your textbook rules out the middle case, so fine. First of all, you got exponentials that look like this. So this is y equals to a to the x, where a is greater than 1, right? Or you've got things like this, right? Y equals a to the x. Well, I'm going to write it in the other color because you can't see that stupid thing. Y equals a to the x, where a is less than 1. All right, that's the blue one. So this one has y goes to 0 as x goes to minus infinity, right? Whereas this one has y goes to 0 as x goes to plus infinity, right? They both settle on 0 in one direction or the other, right? But they both also get really, really large very fast in the opposite direction, right? This is exponential, called exponential growth. Any questions? What's the range for any exponential function in this standard exponential function?
So the range
Yeah, what's the range?
from 0 not touching to infinity.
0 not touching to infinity, right. Yeah, 0 to infinity would be the range. What's the domain?
Everything.
Yeah, everything. Minus infinity to infinity, the whole real line. All real numbers. Right. So I think that's useful to notice. So the domain of a to the x is all reals, right? And the range of a to the x is 0 to infinity, right? Remember this because when we talk about the inverse function, the story flips over, right? Remember that when we talk about the inverse function, the range of the function becomes the domain of the inverse function. So later in this chapter, when we talk about logarithms, we should expect that the domain of the logarithm is like 0 to infinity, whereas the range of the logarithm is all reals. That's what we're going to see later on. All right? Now, so there's a, let's see here, different ways to look at this, but one way we can look at it is if you go through 0, right, you can look at y equals 2 to the x. And you can also look at y equals 3 to the x. I'll do it on my projector over here. Let's see here, 2 to the x and 3 to the x. The 3 is blue, right? So what happens? The 3 is, it goes up above the exponential over here, right? So they cross right here, right? And the 3 goes down here. So here's, so specifically, if you track the point, say at -1, what's the difference? On the green graph, you've got what? -1, 1/3, right? And above it, you have -1, 1/2, right? So the 2 to the x is over 3 to the x to the left of the y-axis. But to the right of the y-axis, right, if we, if I could do it right, if I look at this point, you know, that would be like 1/3, whereas the point directly below it on the 2 to the x is 1/2, right? So 3 to the x is larger than 2 to the x for x positive, right? But 3 to the x is less than 2 to the x for x negative. Now what's interesting, perhaps, is you could look at what's called the tangent line to these graphs. And do you guys know what a tangent line is? I mean, we can't carefully define that in here because we don't have limits, right? But you can get an intuitive sense of it. A tangent line to a graph, if I draw a graph like this, right? And I pick this point, and I want to find the tangent line to that point. It's the line which just kisses the graph at that one point and kind of like resembles it close by. So it's something like this. That's the tangent line. All right? Oh, man. So the tangent line to the green graph and the tangent line to the white graph here, they're related, right? They're not the same. Certainly the tangent line to the green graph, I can't say words, is much steeper, right? The tangent line to the 2 to the x is more shallow. And if you were to numerically study these things, you would find that the slope of tangent line to y equals to 3 to the x is approximately 1.1, basically. It's about 1.1. And if you did the same, you calculated and you could just approximate this, the slope of the tangent line to y equals 2 to the x is approximately 0.7. Right? And you could do that from like looking at secant lines, like we did, calculated the average rate of change, right? You could calculate the average rate of change from like 0 to 1. Calculate the average rate of change from, for both of these separately. And then you could take closer and closer points to get closer and closer to the slope of the tangent. But so if this is the case, right, then it's just geometrically reasonable that there must be some base between 2 and 3, right? There should be some base between 2 and 3 which has a tangent line at the origin which has a slope of between this and that, right? So like I should be able to graph something that's between both of these guys, like this, right? And that middle graph, which I'll call y equals e to the x, well, y equals e to the x, that one has a slope of 1. So it's somewhere between 2 to the x and 3 to the x. And when you study that very carefully, you find out that this e that makes that happen is approximately 2.71, and it goes on and on. All right, so this is, e is for Euler, is in honor of Euler. This is Euler's number. And y equals, f of x equals to e to the x is called the, well, oftentimes I'll say it's the exponential function. This is the most really important exponential function, perhaps, of all of them. So it looks basically like the white graph here, right? But it has a base somewhere between 2 and 3. And this e is not a rational number. It's actually got an unending, unending decimal. If you want to know what it is exactly, you can get well, approximately in the computer anyway. If you take your calculator, go e for exponential, put a 1 in there, I get 2.718281828. That's as many digits as I got on this calculator here, Now, can anybody tell me, so I have given you a geometric motivation for why there should be such a base, and I characterize this as the base for which the tangent line has a slope of 1 at the origin. I mean, at crossing the y-axis. This is not the motivation that your book gives. How does your book motivate the exponential function? Through really, really different way, right? It talks about the problem of interest, right? Now, of course, section 4.1 has other fun stuff about, like, we can do all those games we did before with, like, translating exponentials left or right by, shifting the arguments or the values. We'll get back to that. But this is a, fun application. But at first glance, there doesn't seem to be any connection here between what I'm talking about and what I just did. So compound interest is calculated by the following formula. The amount at time t is equal to the principal times 1 plus the rate over n to the nt. And here, a is, this is the amount after t years. P is the principal. So the principal, that means the original amount either invested or borrowed, right? And R is equal to interest rate per year and N is the number of compounding periods per year, and T is the number of years since the investment was or loan was taken out. So where does that formula come from? Well, I mean, let's just go through the first compounding period. How does it work? You start with P, right? And then you go to what? P, let's suppose we're earning money. Let's be optimistic. So if you have interest rate, whatever, per compounding period, what do? So let's say the interest rate is I, you get I times, if it was 10%, right? And you've passed the amount of time that it takes to earn the 10%, then your investment changes from P to what? To P plus I times P, right? So that's 1 plus I times P. But the amount of interest that you actually earn, you can calculate by the interest rate per year divided by the number of compounding periods. Like, in other words, if you have an interest rate of 12% per year, and you go past a month, how much do you actually get? You get 12 divided by 1. Excuse me, 12%, 0.12 divided by 12. You get 0.01 as the actual interest that's earned after that 1 month, right? So this I is actually equal to your yearly rate divided by the number of compounding periods per year. And let's see here. How to say this? And I said this was after 1 month, right? So I'm assuming n equals to 12, all right? For the sake of discussion. So what's t equal to in years? See, I don't think it's immediately obvious that this formula is the same as that formula. But it is actually. You just have to tilt your head and squint and say, well, that's the principal times 1 plus, r over n, right? Because that's I. And to the 1 power, but 1 is what? 1 is 12 times, 1/12 of a year. My t is equal to 1/12 after 1 month, right? And he is after the second month, you get what? P plus IP goes to what? 1 plus I. Well, anyway, let me not continue this. I have neither time nor interest in doing this. The point is that this formula will calculate the compound interest. All right. What does that have to do with the exponential function? Well, it turns out that if you take the limit as the number of compounding periods goes to infinity, all right, of 1 plus r over n to the nt, that will give you actually e to the rt. So if you let n get larger and larger and larger, so I mean, maybe you go from monthly to daily, right? Then if you wanted to have a good approximation to daily compounding, you could use the exponential function. So if you just wanted to get no r here, if you just put r equal to 1, this is an alternate definition for the exponential is, I'll write it over here. Sometimes I really, really want another board in here. This is one of those times. But anyway, here you go. Another definition of the exponential function, it's the limit as n goes to infinity of 1 plus 1 over n raised to the nx power. So this is another way. Some people use this to define the exponential function. And that has its motivation stemming from the study of interest. If you think about the number of compounding periods going to infinity, then this is the formula that pops out. And you can see that, I mean, this limiting procedure is exactly compound interest formula. But anyway, I think it's more useful for students at your level to not think of it that way. I would just encourage you to think of it as an exponential function with a base of about 2.71. Right? So if I want to think about it graphically, it's somewhere in there, and we can go from there. So I have, let's see here. I think I'm out of time, but that's a good slice of section 4.1 and a little bit of 4.2. So we'll pick up from there next time. Thanks, guys. You got it? It's the...
No, I don't got it.
That's okay. I get it.
With my
Oh, now